Hi everyone, I'm Anish and welcome to PrepFusion. So today we'll be starting the new chapter, that is the state space equation. So my look might be a bit changed because I have changed my glasses and I have cut my beard, that's why. Okay, it will grow soon, don't worry. So yeah, so what we'll do in this lecture is we'll learn about state variables, state equations and state diagrams. So these three are the main fundamental building blocks of this state space equation, right? So for us to understand what a state space equation is, we have to understand these three topics. After that, we'll do questions on these three topics, right? So we'll go slowly, okay, in this chapter, because this is a very fundamental and important chapter. And what happens is that normally we just remember the formulas and the diagrams, and from there we solve the questions, but that's not the correct way to do this, learn this chapter, right? So first we have to learn about the basic terms. So what are the basic terms? As I have already written over there, basic terms are, first is state variable. Now from state variable we'll go to state equation. After defining state variable we will make state equation. Then after defining the state equations we can go to state diagrams. State diagrams is nothing but the SFG, right? Signal flow graph. That is the state diagrams, okay? That will follow this state equations, which follow the cause effect relation, as we learned that, right, on the previous chapter. That in SFG what we used to do is we had SFG, then from the block diagram we wrote the cause effect relation. But here what will happen is we'll have the state equation. From state equation we'll go to the state diagram. We'll have the cause effect relations, and from those we will try to draw the state diagrams, okay? Like what does state mean and what are the meanings of each three terms, we'll just learn in the next few slides, okay? So first, let's say we have a system, right? We have a system. It is taking in some input and giving some response output, okay? Now this system, right, this system will have many components connected to it. Just for example, take a thermal power plant, okay? Now what does it take as input? It takes coal as input, right? And what does it give as output? It gives electricity, basically electrical power as output. But in between, have you ever went to a power plant? You might see that it's a very covered in a very big area, takes up a very big area, and there are so many things, from control systems to furnace to everything, right? There are so many things inside that whole, like that whole thing is known as system, that whole area which it is covered. There are transformers, okay? There are storage, like energy storage also. All those things are over there. So within that system there are so many components in the power plant, right? Now each of one of those components can change the state of the system, right? For example, let's say the transformer is damaged, right? Then what will happen? Then the system will not work, right? We have to again use another backup transformer, another transformer to make the system again work. So the system, the whole system, state of the system, basically the whole state of the system depends on each component itself, right? Now those components we can define them as state variables, right? Like the transformer, okay? Like let's say like the voltage in the transformer, okay? Now let's say we have the temperature of the furnace. If the temperature of the furnace is too high, then something may happen, okay? Something may get damaged or something, okay? So all these things, right, all these things, we may say that those are state variables that define the state of the whole system, okay? For the system to work totally fine. Now what can we define as state variables? Like which things can we define as state variables? The things that have the capability to change the state of the system, not just anything, right? Now let me take the example of a simple RC circuit, okay? Simple RC circuit. So does resistor has any capability to do anything, right? It doesn't. It has the energy dissipating capability, right? It can only dissipate energy, but can it store energy and transfer energy from one place to another? No, it can't. But capacitor has that, right? Capacitor can change the state of the system. It can store the energy, then transfer it to another system, right? so it has that capability. So what we'll assume as state variable is capacitor, right? Not resistor. Okay, capacitor. Now in capacitor, which what will we assume, voltage or current? That will depend. That we will explain. That we will understand in the next few slides or the lectures, right? So from here, I hope you get a brief idea what does state variable mean. Okay. So let me write here is that, let me write what I just explained to you. State variable present in the system. State variable present in the system are responsible for changing the state of the system. Changing the state of the system. Okay. So also another example, what we might say is, let's say like I am here right now, it's suddenly like winter came, it was summer, suddenly winter came. So what I am feeling, I am feeling cold again. So what I do, instead of like wearing this t-shirt, I will wear sweater and jackets. Okay. So my body changed its state due to what? Due to the temperature. So temperature can be a state variable for my body, right? Because my body wants to feel warm again. So what it will try to do is like put on some more like winter clothes to feel me warm again. So that's why like it is responsible for changing the state of the body, right? System. Our body is a system, right? And temperature is the variable. So if temperature decreases, then our body wants to find new clothes, like which we want to wear, right? Winter clothes. So this is also another example of like system. Okay. Of not system, of state variable, right? So temperature can be a state variable for our body, like the variable which has the capability to change the state of the system. Okay. So another example is that, let's say we have this fan, right? So fan, for the fan, like I hope you understand what does a fan does. Fan like takes in electricity. Okay. Then it converts it into it has magnetic energy in it. So it then uses the magnetic energy to produce a rotational motion, right? Kinetic energy. So what is the, how is the magnetic energy getting produced? Due to the flux. Okay, due to the flux. So for the fan, right, we can say flux is a state variable. Why? Let's say the fan is rotating at a fixed speed, so that I can get a fixed temperature at this room. Now what is happening is that, like, now I want to get a different temperature, let's say a lower temperature. So I need more cold air, right? So what the fan will try to do is rotate more. Okay, how will it rotate more? How will it rotate more? So that we have to give it more flux so that it can get more energy, right? So yeah, flux is a state variable that changes the state of the fan to rotate it more, right? To rotate it more and give us more, bring the temperature down. So temperature can also be a state variable, flux can also be a state variable. It has the like changing the state of the fan, right? So temperature, if temperature reduces, so it might say no, it will rotate slow, or whatever, vice versa, whatever you want to do it with respect to temperature. Okay. So whichever variable can change the state of the fan will be called a state variable. Okay. So now one more thing is that state variable, right, they aren't unique. I might say only flux is the state variable, you might say only like both flux and temperature are the state variables. Okay, you can say that, but there has to be a minimal set of state variables that can give us the output. That has to be the one thing. We can set we can take any number of state variables, but there has to be a minimal set of state variables so that we can get our defined output, from the where we can define our system output. That is the one important thing. And you might ask, I am choosing some other state variable, you are choosing some other state variable, will I get the same output? Yes, I will get the same output if both of us are using the correct procedure, right? Why? Because the all the other equations, right, those equations will also change. So according to those equations we will get our output, and at the end output will be same, but the state variables will be different. Okay, we will do examples slowly. From there we will also understand that state variables aren't unique. There can be many form of state variables which we can assume, but at the output, like when we find the output, right, let's say I want to find the output at t equals to 1 second or t equals 2 second. If I choose this state variable 1, and this state variable 2, I will get the same output result at y equals to 1, y at t equals to 1, right, value of y at t equals to 1. So I'll get the same result. Okay, all these things we'll do examples. From there we'll slowly understand. So first point I have to write is state equations aren't unique. State variables and state equations aren't unique, but the final answer, like, or the final output solution of the output will be same. So this was one important thing to note here. Okay, so but what we will try to do is, but we will try to, like, you can select any number of state variables, okay, any number of state variables, but we will try to take minimal set of state variables so that we can define our system output properly. Okay, we can define our system output properly. So this was the thing note for the uniqueness of the state variable. Now what does state equation mean? So let me write what does state equation mean. So this first part will be mostly theoretical. The second part of this lecture will do questions. There it will be more interesting, but first you have to understand each terms, the meaning of each terms, right? So what is state equation? State equation. So state equation is basically a first order differential equation which relates the change of the state variable with respect to the state variable and input itself. All of them are function of time. Okay, so what does state equation means? State equation is a first order differential equation which relates the change of the state variable with which relates the change of state variable with state variable and input, that the input the system is getting, right, with respect to time, as both of them are functions of time. Okay, so let me write it is a first order differential equation which relates change of state variable with respect to, let me write this in full, state variable itself and the input, where both state variable, just one second, let me see if it's recording correctly or not. Okay, sorry for the disturbance. Actually, I was checking whether my mic was recording it correctly or not. So where let me say where was I, like where the state variable and state equation are functions of time. Okay, where the state variable and state equations are functions of time. Okay, so yeah, this was about state equation. So let me give you one example. Like let's say I have one state variable as x, right? State variable is x. Okay, so what will be the state equation for that? Say state variable is x of t. So what will be the equation for this state variable? So the equation for this state variable, right, will be something like this. The differentiation of the state variable with respect to a time should be equals to some constant times the state variable itself plus k2 some other constant times the input, right? Input is u of t. Okay, it's not step, its input is defined as u of t. So yeah, k1 k2 can be 0 or it cannot be, we don't know. K1 k2 can take any values. Okay, so this is what a state equation basically is. So it is a first order differential equation. Okay, so that's why we use the state space method basically to simplify to a like higher order equations to first order differential equations and then solve from there, so that we can analyze the system more in a easier manner. Okay, this is a first order differential equation. Okay, I'm just writing the shortcut. Okay, so after this we have to understand what is a state diagram basically. So what is a state diagram? So state diagram is a pictorial representation of state equations, basically state variables, or you may say state equations. So yeah, that is like what a state diagram is. Basically we will do a simply draw a signal flow graph, right? Just as we learned from the previous chapters. So now like let's revise a bit what I like taught you just now. What we learned three terms, right? First one was the state variable. So state variable present in the system are responsible for changing the state of the system. So they are responsible for changing the state of the system. Those will be our state variables of the system. Okay, so by state I hope you understand whichever affects the system, output of the system or anything, right? That will be our state variable. Now one thing is state variables and state equations aren't unique. They can be I can take a different state variable, you can take a different state variable, but both of us will arrive at the same output. Why? Because the state equations then also will change for both of us, but the output will get same if we do it in the correct, if we choose our state variables in the correct manner. But one thing you have to keep in mind is that we have to take the minimal set of state variables so that we can define our system output properly. At least we have to take the minimal amount of sets which can define my system output. if for example, if I only take for this fan, right, if I only take the flux and don't take any other parameters which can define the rotation speed of this fan, right, don't take like friction, air drag, all those things, now that won't be able to define my output properly. Only taking the flux won't cut it, right? So then it will become wrong, then our equations will become wrong, then our output will get is wrong. Okay, so this thing we have to keep in mind. We have to take the minimal set of state variables. Now we learned what a state equation is. Basically it converts, right, higher order differential equations to first order differential equation. So it is a first order differential equation which relates change of state variable with respect to state variable and input itself. So first of all it converts it to lower order, then the first order basically, then it relates with the state variable itself, like state variables, all of them, all of the state variables, right? I should mention here all of the state variables. Like let's say this fan has 3 state variables, but I am trying to write the state equation for the first one, right? So the first state variable relation, the differentiation of that will be related with all of the state variables. Here we have x1, x2, x3, all of them, right? K1, x1, k2, x2, k3, x3 plus k4 u of t, that is the input. So yeah, this was the relation for the state equation. Okay, and state diagram is very simple. Just convert the each state equations, right, or the state variables into a SFG, signal flow graph, or a block diagram for easier understanding. Okay, so yeah, these were the 3 terms. Now like why are we using the state like state space, right? Why are we studying? To analyze the system, as I mentioned earlier also. But you might ask that we can already analyze the system using classical method. What is that method? That is the transfer function method. Okay, let me write this properly. Transfer function method, right? So why am I using this state variable method? There must be some limitations in the transfer function method. First limitation that I like right away says that it is only valid for LTI systems. Okay, so classical method is only valid for LTI systems, whereas state variable method is valid for non-LTI, like non-LTI systems basically. Okay, non-linear systems it is valid, linear invariant system it is valid, time invariant system it is also valid, right? Time variant, time invariant, both of them it is valid. Okay, also classical method is only valid for single input single output system. What do you mean by that? Like it has only a single input and we take only single output. Like we have done few examples of psus system, right? So classical method is only valid for that, whereas state variable method is valid for both CISO and MISO. We'll do few examples. Like MISO is multiple input single output systems. We'll do few examples on MISO. There we'll understand like what do we mean, like how do we analyze a system which has multiple inputs and single output, or which has multiple outputs and single input. All these things we can do it with state variable, but with classical method we can't do. Okay, so it is another important factor to note. Also, classical method do not describe the internal state of the system or the initial value of the system. Like this is understandable, right? Why? Because if I am using classical method, it uses the transfer function, and transfer function what we do is make the initial conditions 0. So we can't find the 0 input response, right? 0 input response where the initial conditions are 0, or we can't do the analysis if we have some initial value of the system becomes non-linear, then we can't analyze the system. Okay, for classical method, whereas state variable method describes the initial value of the system. State variable method we can analyze circuit with initial value and the input simultaneously applied to the system, right? All those things we'll do examples from there, you will understand, but these are few points to know. Now let's do few questions. From here your understanding of state variable, state equation and state diagram will be more clearer. Okay, so what is the first question? So first question is that we have to draw state diagram and find state equation for this input and output as they are related like this. Okay, the relation between the input and output is a second order differential equation. So we can solve this using Laplace, directly find the transfer function. Okay, but we will not do this with Laplace, we'll do this with state space. So we have to draw the state diagram, also find the state equation. So first we'll find the state equation, then we'll draw the state diagram. But first, for finding the state equation, we have to take few state variables. Now how many state variables will I take? So just keep in mind, like the minimal set of state variables we have to take is will depend on the order of the differential equation. So here, what is the order of the differential equation? It is 2, right? It is 2. So I hope you know how to find order of a differential equation. Okay, just the highest differentiation term, right? That will be the order of the differential equation. So here the order of the differential equation is 2. So how many number of state variables we have to take? We have to take 2 state variables. We can take more than 2, but we cannot take less than 2. Minimum we have to take 2 state variables. Now the first one, obviously I will solve. You don't have to solve by yourself, okay, because you don't know anything right now. So there can be many methods of assuming a state variable, but this is the first method that I will show you. Okay, this method we will use this throughout this lecture, and after next few lectures I will teach you more methods of how to define state variables, right? But this is just the first method. Generally this is the 90%, 80% of the cases we use this method only. So what do we do, how to solve this question? Step 1 is define state variable, right? We have to define state variable. Now what do I mean by state variable? Who can change the state of the system. Now the first method, what we do is we assume x1 as state variable, like first state variable x1, which is equals to the output itself. Okay, we assume this one, right? Now what we do, we differentiate our output, right? dy of t with respect to time. What do we get? We get dx of dt, dx1 of dt, that we can represent as dot. Okay, generally differentiation we represent as a dot. Okay, now what is this differentiation equals to? It is equals to, now what we do is we equate this x1 dot, right, equals to another state variable, that is x2. So this is the second state variable. Now if I again differentiate this, right, again differentiate this equation, what do I get? I get x1 double dot, but I won't write it. What I will write is x2 dot, because this x2 equals to dy of dt. If I differentiate this again, so here we will get a dot. So this becomes x2 dot. Okay, so after this we don't have to assume a new state variable, because already we have reached our highest order of y, right? Differentiation of y. Okay, so this is the minimal set. So let me write number minimal number of state variables simply equals to order of the differential equation, right? Now our state equations will be first order differential. We have converted to first order differential equation. How? Let's see. So what is the equation 1 basically? Like state equations. So we have picked our state variables. Now let's write the state equations. So what are our state equations basically? So our state equations, right? So yeah, this is the first state equation that I see, that it is relating my state variable, like the differentiation of the state variable with another state variable, and input is like multiplied with 0 right now. So this is the equation 1. x1 of t should be equals to x2 of t. So this is one state equation. Now do we have another state equation? So this one, right? What I will do is, okay, where was I? Okay, I was here. So I will write this equation, okay, in terms of like the input and y of t, input in terms of the input and the state variables. This equation. So let me copy these equations first. This is the first equation. Now how to convert this equation? So what is this? This is x1 x2 t, x2 dot t, right, as I wrote here, right? So this I can write as x2 dot t plus, what is this? I can write this as either x2 or x1. So x1 dot, but I won't write x1 dot. Why? Because I have to find the relation like this. Okay, state equation relation, right? There shouldn't be any differentiation term in this right hand side. Only one differentiation term will be in the left. There won't be any differentiation term. There will be only state variables on the right hand side. Okay, so I won't write here x1 dot. What I will write is x2, right? Because this is equals to x2. Now what is yt equals to? As I previously assumed, right, that yt equals to x1t. So this will become our x1t, because we don't have output in the state equation. Okay, we have only state variables and the input. So that's how we will relate, and this is simply equals to u of t. Okay, so what is x2 dot t? x2 dot t equals to minus of 2x1 minus of x2. Okay, plus u of t. Okay, so this is minus of 2x1 minus of x2. This is also t actually. Sometimes what will happen, I will not write this bracket t, right? That is just understandable that it is function of time. So this is our second equation that we get. Okay, what we can see, this is also a first order differential equation. Here we have x2t, and we have it in terms of our state variables and the input. So now what I can do is write this in like matrix format. Okay, so we will see. Also I will define it to you, what the significance of matrix. For now we're just understanding these terms, what state equation is and all these things, but later I will write this in a more structured manner, like how, what is the order of the matrix, how to define those things, right? All these things we'll learn. So yeah, this is basically the equation. Let me copy this equation again. Okay, this is, let me write this here. Okay, this is the first one. So I can convert this into a matrix format. These are my state equations. These are basically my state equations, where I converted a higher order differential equation into a first order differential equation. Now how to write this in matrix format? So just like see it for now. Everything, the order and all those things I will explain, like why are we getting a 2x2 matrix this time, and why is the input multiplied with a 2x1 matrix this time. All these things we'll understand like in next few lectures, right? This lecture is just for basic understanding of state equation and state diagram. So how will I convert? What I will write is the state equation here. So what is the, on the LHS of the state equation, it is the differentiation of the state variables. So this one will be x1 dot of t x2 dot of t. Okay, and on the right hand side, what do you have? So we have, what I see is x1 dot of t is only dependent on x2 dot of t. So this, right, this is multiplied with only x1 of t and x2 of t. Like this is the, like these have some specific names, right? These has some specific names. Like these are only column matrix only. Okay, these two. So all these things I will teach you in more like formal manner, but for now just understand we'll have x1 and x2 here. So what do I multiply to only get a function of x2 and x1? The coefficient of x1 will be 0, so this will be 0 and this will be 1, right? Because it is equals to x2 itself, so this will be 0 and 1. Now this x2 dot, right, how is it related with x1 and x2? So this x2 dot, what I see is x1 it is related with like it is multiplied with -2, and with x2 it is multiplied with -1. So -2 and -1. Okay, so this is the relation between x1 and x2. Okay, this is the relation between x1 and x2. Now how are our state variables related with the input? So this will again be a column vector. This will be a 2 cross 1 like matrix basically. Why? We'll learn all this, right? But for now, just let me go with the flow of the like question and solve few questions so that you can get a feeling of state equation and state diagram. So again, how to write this? So this, right, x1 dot is not related with the input, right? Here we don't have any input term, but here we have input term whose coefficient is 1. So I can write this as 0, 1. Okay, so like the what we are seeing is a pattern. This pattern will follow the matrix format that I'm talking about. So this is the state equation. Okay, now one more thing to note here is that the state equation, right, state equation depends on the initial value and the state variable and input, not only on the state variable and input, because this x1t, right, this x1t initial values of the state variable itself. Okay, so this x1t may have initial value, right? So that also may cause change in the state equation. Okay, so like that is also another important point to note itself is also. So because like this has some t equals to 0 value, like for example, if I take the current as the state variable for an inductor in a simple RL circuit, so if it has some initial current through it, so that will change my state behavior throughout the whole system for the t greater than 0 plus, right? T greater than 0 plus, if I connect a source, that will change the behavior of the output. Okay, it will not be the same if it didn't have any initial value. So state equation also depends on initial value of state variable. Okay, so yeah, this is one important point to note is that now what we will do is the second part of the question, that is we have to draw the state diagram. So how to draw the state diagram? So basically for drawing the state diagram, what I have to do is convert this into Laplace domain. Why? Because SFG has like Laplace domain terms, right? So that's why I will convert this into Laplace domain first, the state equations, that is, then I will solve. So what was my first state equation? It was x1 dot. Also one more thing I forgot to tell you is, if you expand this, right, row wise, if you expand this row wise, you will see x1 dot is related with this, like whatever you got in this equation, and x2 dot is related like this with this equation, right? So this is basically the state, like the equations, right? The matrix form. From matrix form we can go to the normal state equation form, and from state equation we can go to the matrix form. Okay, all these things we will do more questions, and I will explain it to you more formally. From there you will understand. So now, what is x1 dot t? It is equals to x2 t. This is the first equation. So what is x1 dot? It is basically dx1. Okay, this t dt equals to x2 of t. Okay, so now what do? We take the Laplace of this, right? We take the Laplace of this. So if you take the Laplace of this, what do we get? I get x into x1s. And do I get anything else? Yes, I get x1 of 0, right? Like you might say, when I like taught you in the first basis of control system, there I may not have written this x of 0 term for differentiation. Why? Because there, right, we were calculating the transfer function, and for calculating the transfer function, what do? We make the initial condition 0. But just to remember this is very very important, that if we take the Laplace of the unilateral Laplace of a differentiation, then we'll get our Laplace transform like this: s times x1 of s minus the initial value of that variable, right, x1 of 0, which will be equals to simply x2 of s, which will be equals to simply x2 of s. Okay, so these things you have to keep in mind. Okay, so here, as state equation takes into factor the initial values as well, so we will consider the initial values. There we ignore the initial values. So what does my x1 of s become? X1 of s simply becomes 1 over s times this x2 of s plus x1 of 0s. Okay, so this is like important factor. So how can I divide my x1 of s? Is this is 1 over s x1 of 0 plus x2 of s divided by s, right? So this is the cause effect relation that we were looking for, right? So this is the cause effect relation. So what are the cause? These two are the cause, right? These two are the cause, and this is the effect. Okay, due to these two things we are getting this effect, right? So how will I draw the SFG for these equation only, this equation only? So what do I have? I have two variables, right, like this. So one is x1 of 0, which is divided by s, and here let's say we have gain of 1, which is added with x2 of s, whose gain is 1 over s, and we divide it by s, and we get x1 of s. So these two, right, these two are coming here, combining with x1 of s. Now you might ask why I wrote 1 over s over here and 1 over here only. Why I wrote like this? Because, right, one thing we know, that due to this, right, because x2 is differentiation of x1, that's why I had to write 1 over s. To get from here to here, I have to integrate this. I have to, sorry, what I called, to get from x2 to x1, I have to simply put a 1 over s term, and I will get 1 over x1, right? I will get x1. But from here to here, we only have the initial condition. Okay, the initial condition is not something that we do integration or differentiation, right? That is just a constant term. So I multiply directly 1 by s with it. Okay, and here I multiply it with gain. This is just the convention that we do, so keep this in mind. Okay, keep this in mind. So what is this? This is not the complete state diagram, right? This is just the state diagram for this particular equation, only the first equation, but this is the building block for understanding state diagram. state diagram for this equation. Okay, now let us use the basically the second equation, right? What is the second equation? So one more equation, what we have is, what we'll do, we know that this x2 dot, right, x2 of t equals to d square y by dt square. Now what we'll do is we'll assume another variable as x3 of t. Now this is not a state variable, we just assume it for now for our ease of our calculation. So assume, okay, we'll just assume it now. Now what is our like the second state equation? It was something like this, right? It was, okay, let me copy this. Yeah, this one. So instead of x2 dot, just for our ease of understanding, I will write it as x3. So instead of x2 dot, I will write this as x3. Okay, so x3 of t equals to all this. So again I will bring back my previous state diagram, this one, right? This one is the building block. So what things are getting added over here? So one thing to note is that due to this x2 dot, right, due to this x2 dot also, we'll get an initial value over here. So that thing I hope you are able to understand. So we'll get an initial value here. Let me draw it with different color. That will be added with this x2 of s, x2 by s. Okay, now what more things we are getting added? If you are not able to understand this, I can solve this for you. Okay, so here, write this one. I can write x s times x2 of s equals to minus x2 of 0 equals to x3 of s. Okay, so what will be my x2 of s equals to? It will be equals to x2 of 0 by s plus x3 of s by s, right? So yeah, from here you are able to understand that this x2 of s will also get added to this x2, right? X2 of 0 will get added to this x2 of s. So I'm deleting this. I hope you are able to understand. Now also we have to add x3 by s. So this will be my x3 and this is my gain of 1 by s. So x3 by s is also getting added. Okay, x3 by s is also getting added. Now what is x3 equals to? So x3, right, I will write this in the next page. x3 is equals to this one. So this one was just for the x2, right? This one was just for the x2. Now what is x3 equals to? x3 is equals to this. Now let me again convert this into Laplace domain. So u of s. Okay, so now like again modify this state diagram. So again we have a cause effect equation, right? Cause effect relation here, right? So this x3, how we are getting the effect? Due to this, we are multiplying minus 2x1, like we are providing it minus 2x1. So x1 is here, x1 is here, right? So I will draw it here and write the gain as minus 2 because it is minus 2x1. Also what we are getting is minus 1x2. So again, like shift this a bit. This is minus 1x2, right? And we have the input also. So input, right, will be on the left hand side always and the output is on the right hand side always. That's the general convention. So can take this here. this is my input. Okay, this is my input. So yeah, now what I can do is, instead of writing this x3, right, what I will write here is s times x3, s times x2, because x3 was that only, right, x3 was that only, x2 dot was x3 equals to, so that's why I wrote this as s times x2. So with x2 we will add this initial term, and s times x2, if I multiply with 1 by s, I get x2 only, right? So yeah, that's how we draw the state diagram of the of this state equation. So that's how you proceed, right? First, what you do, use draw the state diagram for the first equation x1. You go from x1, then you go to x2, but this is the main thing. Okay, this is the main building block that you have to understand. Then you go to x2. Basically you solve for x2 first. Okay, you assume another variable. Now if you have like more variables, then the last variable, what you will do is use one extra unknown. Assume, like, if my order is 3, I will assume x4t equals to x3 dot, and from there I will solve. Okay, assume this variable. Then after solving the x3, right, I will replace this with the previous variable. Okay, not taking extra variables. Okay, like this I can solve. So first I will solve this, then I will solve that, then I will solve the final equation. Okay, by using this method, what we can do is simply write the equations like this in form of this one, right? So x1 dot will be equals to x2, then x2 dot will be equals to x3, like that we can go. But the last state variable will depend on everything, input and all those things. Okay, so this is the just the one method, but all the time we can't solve it like this. We have to use, if we can't solve it like this method, then we have to use another method. So yeah, this one was the basically the state diagram for this. Now what we can do, we can solve for the state diagram using another method also. So state diagram using method 2. So for that, first I have to write the differential equation, basically the output differential equation that we got right here, this one. So this is the differential equation. So this is basically the, what is the order of the equation? Order is 2. Order is 2. So in this method 2, right, what we do is, we first draw the state diagram and we write the 1 by s terms according to the order of the differential equation. So here, right, we have order 2. So there will be, from here we will understand that there will be 2 1 by s terms of 2 1 by s terms. So step 1, what will be my step 1? Here I will have an input, and in between I will have 2 1 by s terms. Okay, 1 by s and 1 by s, and here I will have my output. I'm not talking about output yet, okay, because I haven't wrote the written the output equation. That we will do in the next question. So here we will have 2 1 by s terms. Why? Because we will have to integrate 2 times. We'll have to integrate here 2 times, right, to get to y of t only. That's why we get 2 1 by s terms. Now in step 2, what I will do is define the state variables. So copy this again. What I will do, define the state variables basically. So what will be my state variable? I will assume, as I assumed previously also, this one will be my x1 of s. Now this one, right, this one was x1 of dot t. So in Laplace it will become x1 of s, or we can define this as x2 of s also. Okay, and what will be this one? This would will simply be equals to s times x2 of s. you just see that if I multiply 1 by s with sx2, I get x2 of s. If I multiply 1 by s with sx1, I get x1 of s. So from here you can understand, right? So the differentiation representing that, like here we have s square term, we have just s term because it becomes s square y, this becomes sy, and this is just y. Okay, so this is just x1, this is s times x1, this is s square times x1. So that's why we get x1 here. Now this is s times x1 and this is s square times x1. Okay, I hope that's how you're understanding. Okay, and this is the input basically. Okay, so yeah, I hope you got it how I wrote this, right? Now let me write the state equation again, the state equations again. So let me, this one was the, no, this one wasn't the state equation. Yeah, this one, right? Let me write the state equations again. What I will do is simply take the inverse Laplace of this. Okay, so taking the inverse Laplace of this, s x1 of s equals to x2 of s. So this is one equation. So from here I have written it directly, right? That is this s x1 of s equals to x2 of s. From here I have written it, okay, because of the first equation. So let me write equation 1. Okay, else I wouldn't have connected them also, but as they are connected, that's fine. Like this is proving that equation, right? Proving the diagram basically. Now solving the second equation. So let me mark it like this. Let me take the Laplace here. So this is x2 of s times s equals to minus 2 x1 of s minus x2 of s plus e of s, right? So here s x2 of s is this one, okay, but we have relations like this. So again, this is the step 3, relating the final equation, right? Relating the final equation. So I'll copy this again. So this is sx2 and this is x2 of s, right? And this is x1 of s. Now what this equation is telling us, that sx2 equals to minus 2 times x1 of s. So here, right, we have to put in a minus 2 here, minus 2 times x1 of s. And what is this x2 of s equals to? This x2 of s, right? x2 of s, sorry, like how is it related with x2 of s? Simply minus 1. So let me bring this top over here. Into minus 1 of minus 1, right? And this is also related with input, with gain 1. So I'll connect the input with gain 1. Okay, so basically this is how it is related with the this is a state diagram, right? So this is how it is related with the input, the state variable, state diagram. So this is the state diagram. So in state diagram I don't have to write the output, okay, I won't draw the output, but the output will just put it as 1 into this x1, because x1 equals to y of t only. So this is a state diagram. Without output. Now what I will do, I will do the step 4. step 4. So it is with output. How it is with output? So basically, what is that first equation that we wrote, right? It was x1 of t equals to y of t. So x1 of s equals to, taking the Laplace transform, equals to y of s. So this becomes my y of s, and this is equals to 1. Okay, this is equals to 1. So yeah, this is how the state diagram is with output. So like, but the first thing is we haven't considered the initial conditions. So what we will do, like, this is just step by step process, and you have to remember this step. You have to remember this. So the final step will also be like, these are also without the initial conditions, output and initial values, right? But without initial values. But now we have to consider the initial conditions as well. So everything will be same, just with x2 of s and x1 of s will add the initial values, which are divided by s, right, as we learned in the previous method, right? So this is just a method that you have to remember to draw the state diagram. Okay, this is a method. Okay, if you don't want to solve it like that using basics from the method 1, this is a shortcut, but you have to remember this method, right? That when you have to add in few things, so initial conditions will add at the end, adding initial conditions. Okay, so we have to add the initial conditions. So how I will add it? So here, right, I will have x2 of s and x1 of s, and okay, let me draw it a bit small, also, and this is getting added, and this is getting added. So x1 of 0 by s and x2 of 0 by s, this is 1 and this is 1. Okay, so yeah, this is the complete state diagram basically, okay, of this state equations of this question basically. So I hope you understand how I went through step by step and break it down. So what did I do? So basically, first we have to draw the state diagram, but before that we have to find the state equation. So I found out state equation by using this particular method. Okay, using this particular method. What is this method called? It is called the Cascade canonical method. So you will not understand this, so later I will teach you all these things. Okay, so here what it did was, what was the how to use this method is simply assume the output as one of the state variable, then differentiate that, and that differentiation will be another state variable, and then again differentiate that, and that will be our final state variable, because our order was 2. Okay, so we had 2 state variables, right? 2. So this was the first thing. So we understood that using the minimal number of state variables what we can have is 2, right? So order of the differential equation will be 2. Okay, so the state equation we get is like these two. Okay, from there we solve in matrix format. So as we do more questions, you will understand how to write this in matrix format. I will explain it to solving more questions. This one just was the example problem to understand what a state equation is, how to use mathematics using state equation, right? So that was more important. So then we solve for the state diagram. We have to move to Laplace domain, because signal flow graph is generally written in Laplace domain. So when I move to Laplace domain, if I take the inverse Laplace, the Laplace transform of this differentiation, right, we will have an initial term. Okay, as we are taking the unilateral Laplace, this will be taught to you in signal systems. Okay, but for now, just understand we will have an initial value. Okay, now that will like our equation will be like this, cause effect relation. Now from there we'll draw the SLG for that particular equation, and from slowly we'll, that this is the building block. From here we'll build this equation, and from here we'll build our whole equation, right? So these things I've already explained it to you very clearly. Now we solve it using method 2. That is basically shortcut, but you have to remember the method. What do we do? First, what we do is write the number of 1 by terms as the order of the differential equation. Here the order is 2, so I write it as 1 2 2 1 by terms, right? Then step 2 is this one. Okay, step 2 is this one. What we do is write the state variables, right? State variables and how they are related. So this relation, right, comes with respect to this first equation. So let me write this here only. Okay, and the second relation we solve it in the second step. So each step you can solve each equation. This one was the first equation. So here as x1 we got as x2, and here we got the relation between the sx2 and other state variables x1, x2 and u. So we wrote it. Okay, we got the state diagram. Okay, and then we solve the step 4. So in step 4, right, we do like wrote connected with it with the output. So output was the output equation, simply this one, right? The first equation that we wrote. Simply take the Laplace transform and we get this equation. Okay, then we add the initial conditions. That how, why are we adding the initial conditions? Due to that Laplace domain, right, thing, and it will be added with the state variables itself. That also we understood in the method 1. So this you have to remember. Obviously there is no concept, this you have to remember. Okay, so I think like this lecture has already gone long. So in the next lecture what I will do is calculate the output using the state diagram here, as I have written, right, x of x1 of t, x to y of t. That we'll do, and also we'll do few other things with respect to initial conditions, how will be our output, and with respect to input and output. Okay, all these things we'll learn the next lecture. Okay, so yeah, thank you for watching. सोच रहा चला जाएगा